Good morning. This is Dr. Shankaraiah, Assistant Professor in Department Physics. So, in the last couple of lectures, I have discussed about brief history to computer simulations, and also I have also discussed about how we can generate ensembles, which are familiar in statistical mechanics, and how can we generate ensemble and then calculate properties, macroscopic properties of a system using different computer simulation techniques. So today I am going to discuss about Monte Carlo simulation, which is computer simulation techniques that can be used to study or obtain different macroscopic properties of a physical system. So Monte Carlo is a numerical technique that makes use of random numbers to solve a problem. So if we want to study or obtain any macroscopic properties of a system, we can use Monte Carlo technique. It makes use of random numbers. So this is also called stochastic simulation technique. This is not deterministic numerical technique, whereas molecular dynamics simulation techniques are deterministic, where we solve Newton's equations of motion. But Monte Carlo simulation is a stochastic simulation technique. That means we use random numbers to study or to solve a problem and to obtain macroscopic properties. Historically, the first large-scale Monte Carlo work carried dates back the middle of 20th century. So the first Monte Carlo technique applied successfully around middle of the 20th century. So the first people who started this Monte Carlo technique is Stanislav Ulam, Newman, and Fermi were the first to propose and employ the Monte Carlo method as a viable numerical technique for solving practical problems. So this is the first set of people who proposed a numerical Monte Carlo numerical technique, and they also employed this Monte Carlo method to solve a problem. And they proposed that you can apply this Monte Carlo numerical technique to solve a problem and obtain different macroscopic properties. So the earliest work that is published on Monte Carlo is perhaps the paper by Metropolis and Ulam in 1948. So this is the first paper, the first work done by these people and using Monte Carlo technique, and that is published in 1949. So for carrying Monte Carlo simulation, we require sequence of random numbers, as I mentioned, and these random numbers should be independent, real, and they should be uniformly distributed between 0 and 1. So if we are generating a random numbers, all these random numbers should be strictly independent and they are real and uniformly distributed. If you generate a sequence of 1000 random numbers and plot them, then you should find them all the random numbers are equally generated. They should be we should not find that some numbers between 0 1 are generated more and some numbers are generated less. No, all the numbers generated between 0 to 1 should be uniformly distributed. Okay, and these sequence of random numbers, if and only if generated by a random physical process like radioactive decay, thermal noise in electronic devices, cosmic ray arrival times, or tossing of a coin. So if the random numbers generated by a real processes, like for example, simple is tossing of a coin. Toss a coin and the outcome will be either head or a tail, and generate one random number. So the random number generated by this experiment of tossing of a coin, then we can call those random numbers as strictly random, because these are generated by physical process. These phenomena are known to be truly random, at least according to the present day theories. Okay, so we are going to take random numbers generated by these experiments. For example, radioactive decay you can consider, and then thermal noise generated in electronic devices, cosmic ray arrival times, and tossing of a coin. So you can generate random numbers by using these experiments, and these random numbers generated from these experiments are truly random as per the theories. So you generate once and for all a fairly long sequence of random numbers from such a physical process. With these, all these physical processes are random. Okay, so we are going to generate a large sequence of random numbers from this random physical process, and we are going to keep them in a hard disk. So employ these sequence in your Monte Carlo simulations, and this is always a safe procedure. So I've said that, I mentioned that Monte Carlo simulation technique is a numerical technique that makes use of random numbers. So, and these random numbers will be truly random only if we generate them from a random physical process. As I mentioned, few examples. Okay, so if we are going to use only these truly random numbers generated by this random physical process, then whatever results we are going to obtain using this sequence of truly random numbers in Monte Carlo simulations, we will get correct results, and this is a safe procedure. Indeed, table of random numbers were generated and employed in early Monte Carlo practice. So, using these this kind of random physical process, a table of random numbers were generated, and they were used in Monte Carlo simulations in the early times of this Monte Carlo simulation practice. So there are many other random physical process. For example, census reports, telephone directories, spinning wheel, automatic electronic roulette, radioactive delay, thermal noise in a semiconductor devices, and were employed to generate large table of random numbers. So there are many different random physical process from which we can generate a sequence of truly random numbers. So some of them I have mentioned here. So a table of random numbers is useful if the Monte Carlo calculation is carried out manually. However, for computer calculations, use of this table is impractical. So if we are going to calculate Monte Carlo, we are going to use Monte Carlo simulations and going to calculate a macroscopic property manually, then we can use these random numbers that are generated by using this random physical process. But we are going to solve a problem using Monte Carlo simulation on a computer. If we are going to solve a simulation on a computer, we need to store all these table of random numbers on a computer. So storing a large sequence of random numbers on a computer is impractical, or it's very difficult. So to store this large sequence of truly random numbers generated by a random physical process, we need a computer having a relatively large internal memory. If we have a computer that is having a relatively small internal memory, it cannot hold a large table of random numbers. So to keep these truly random numbers that are large in sequence and generated by a random physical process, we need a computer with large internal memory so that we can store all these truly random numbers on that computer and which we can use them in Monte Carlo simulation. One can keep the random numbers in an external storage device like a hard disk or a tape. But then constant retrieval from these peripherals would considerably slow down the computations. So we can store these random numbers instead of random internal memory. You can store these random numbers on a hard disk or a tape of a computer, and then while we are carrying out the simulation, we can retrieve the random numbers whenever we need from these peripheral devices like hard disk. But In simulation, we are going to use these random numbers very frequently, and we are going to retrieve these random numbers from these peripherals, so that retrieval can slow down the computations considerably. So hence it is often desirable to generate random numbers as and when required, employing a simple arithmetic operations that do not take much computer time. And algorithm itself does not require much memory for storage. So it is going, the computer simulation is going to slow down if we are going to retrieve the random numbers that are stored on a disk of a computer. So hence it's important, or it is desirable to generate a sequence of random numbers when we require, okay, in our simulation. So we can do that by using some simple arithmetic algorithms, simple arithmetic operations, and these operations do not take much computer time, and the algorithms which we are going to use to generate these random numbers do not require much computer storage. So we are going to do this because if we are going to store the truly random numbers and retrieve these truly random numbers whenever we require in simulation, is going to slow down our computations. So these numbers generated by deterministic algorithms are therefore predictable and reproducible. So if we want to use the truly random numbers generated by random physical process, we need to store them on a disk of our computer. And whenever we need a random number, we can retrieve this truly random number that is stored on a disk, and we find out that it is going to slow down our computation. So that is the reason why we are going to take an alternative step to generate these random numbers using deterministic algorithm that doesn't need lot of time, and it is not going to take more memory on the computer. So we are going to generate these random numbers using a deterministic algorithm, and therefore these random numbers generated by deterministic algorithm are predictable and reproducible. Hence, by no stretch of imagination, we call them random, because we are going to generate these random numbers by using a deterministic algorithm. We cannot say them truly random, right? We shall call them pseudo random. So we are not going to say random numbers generated by this deterministic algorithm as truly random. We are going to call them as pseudo random numbers. And we need to test these random numbers or pseudo random numbers to find whether they are uniform or are they truly random. So we need to check, are these random numbers have to go through some test to check the randomness satisfactorily. In fact, it is always a good practice to check if the sequence of random numbers you are going to use in your simulation goes through several standard tests of randomness. So if you are going to use the pseudo random numbers which were generated using deterministic algorithms, we need to check that these pseudo random numbers are uniformly distributed, and we are going to do it by using several standard tests of randomness. So it is also desirable to devise special tests of randomness depending on the particular application we have in mind. So whatever pseudo random numbers we have generated using deterministic algorithms, these random numbers have to undergo through standard test of random numbers, and depending on what kind of problem we are going to use. So basically we generate random numbers using there are different techniques to generate random numbers. Here I am mentioning few generators that are used to generate random numbers. For example, congruential generators, Masaglia lattice structure, register generators. So these are few generators, but there are many generators. Whoever wanted to use these random numbers, they themselves can predict or generate and create an algorithm to generate random numbers. And the random numbers which were generated, which we call it as pseudo random numbers, they have to go through standard tests of random numbers so that they are uniformly distributed and are truly random. So we can use different techniques to check the sequence of numbers are random. So we have discussed that so Monte Carlo simulation is a numerical technique, and we are going to use random numbers to solve a problem. And we have discussed how do you generate random numbers and what are the tests these generated random numbers have to go through. Okay, so now we are going to use these Monte Carlo simulations. So we are going to use this Monte Carlo simulation to study phase transitions in a magnet, which I have mentioned in the first lecture of this series. So I've mentioned that we are going to use Monte Carlo simulation to study phase transitions in a magnet. So we are going to use a model that is familiar in statistical mechanics, which is called as Ising model. So we are going to apply Ising model and use Monte Carlo simulation technique to study phase transitions in a magnet. Okay, so we already you can consider iron. Iron is a metal that has free electrons. The outermost orbital couple and the electrons can move freely in the lattice. So these unpaired electron spins can couple and align. So spin of each unpaired electron. So spin of each unpaired electron. So each electron has a spin. It can be either oriented up direction or down direction. So each spin of this unpaired electron can couple. And these spins can orient in different directions. Either they can orient in opposite direction, or they can orient in same direction upward. They can orient in same direction downward. Right? So these unpaired electron spins can couple and align into different directions. So each spin has a tiny magnetic moment. Each spin has a tiny magnetic moment, and the summation of these spins, that means when the spins align into some direction, the summation of all these tiny magnetic moments can result into a macroscopic magnetism. So I am saying that I have a metal. I'm taking iron, which is a metal, has unpaired electrons, and each unpaired electron has a spin. And this unpaired electron spin can couple and orient. So there are many unpaired electrons. So these electron spins can couple and align to different directions. So when we sum over all these spins, that is called as the spin is called each spin has a magnetic moment. So when we sum over all these tiny magnetic moments, then we find out that there is a macroscopic magnetism. Okay, so in the year of 1923, Professor Lenz proposed a very simple model of magnetism to his student Ising. So Ising solved this model analytically in one spatial dimension, and that time, ever since, this model is called as the Ising model. So in the Ising model, a spin has only two states. As I mentioned, up and each spin has two states, up and down. Let us denote the spin variable by the symbol SI. And in the model, we say that SI can take only values of +1 and -1. So when the spin is oriented in the up direction, we are going to take it as +1. And when the spin is oriented in down direction, we are going to take it as -1. So we organize the spins on a lattice, and the index I refers to the lattice side. So the lattice can be in general d-dimensional. It can be 1 dimension, it can be 2 dimension, it can be 3 dimension. So whatever dimension you are going to consider, spatial dimension you are going to consider to solve this Ising model, you can place a spin on each lattice side. Okay, so SI, I refers to the lattice side. So we are going to take, for example, a 2D lattice. Square lattice. Okay, of 5 by 5. So each lattice site is going to have a spin. Each lattice site is going to have a spin, and the spin can be either oriented in up direction, or it can be oriented in up direction, or it can be oriented in down direction. If the spin is oriented in up direction, we are going to take a value of +1. If the spin is oriented in down direction, we are going to take a value of -1. If it is down, it is -1. If it is up, it is +1. So all the lattice sites are going to have spin, and each spin can be either up or down. Depending on up or down, we are going to take either +1 or -1, right? So to understand the phase transition in a magnet, we are going to apply this Ising model, and we are going to consider 2-dimensional lattice or 1-dimensional lattice to solve this Ising model. Okay. So let I and j refer to two nearest neighbor sites on the lattice. So we are, as I mentioned, we are going to take 2-dimensional lattice, and 2-dimension. So when I say 2-dimension, I need two indices, right? So I need two indices. One is for row and one is for column. So I and j, I am taking two indices to refer row and column, and here I am taking two sides, neighbor, here one side, and this will be the neighbor side to this side. Okay, so SI, let me take SI as the variable on site I, and SJ is the variable on nearest neighbor side J. Okay, so these are the spins on two lattice sides, neighboring lattice side. So energy associated with the pair of nearest neighbor spins is given by this. This is the energy associated with the pair of lattice. Okay, so that is -j SI SJ, where SI is the spin on site I and SJ is the spin on site J. So this is the energy. So thus when two spins are aligned up or down, the energy associated with them is -j. If all the spins are aligned in the up direction, let me take two spins. So SI is +1 and SJ is also +1. So 1 into 1, 1. So that will be -j. Either oriented in up direction or oriented in down. If they are oriented in down direction, two spins, -1 into -1 +1. So I will again get -j. So when the two spins, neighboring spins are aligned, both aligned in up or both aligned in down, the energy associated with them is -j. When not, that means when the spins are not aligned in the same direction, they are aligned in random directions. They can be aligned in, the two spins can be aligned in this direction, or the two spins can be aligned in this direction. So in this case, the energy associated is +j. The -j is when the spins are aligned in both in up direction or both in down direction. When the spins are oriented randomly, one is up and one is down, or one is down and one is up, then the energy associated with these two neighboring spins is +j. So the value of j measures the strength of the interaction between these spins. So if j is positive, we are saying that the spin-spin interaction is positive. We are going to take j as positive. the interaction is ferromagnet. So if we are going to take the spin-spin interaction as plus, then the interaction is called as ferromagnet. If J is negative, if we are going to take the interaction between the spin as minus, then the interaction is said to be antiferromagnet. So we are going to consider J positive, which is going to be said as ferromagnetic interaction. And then you can see here in this figure, the figure depicts 1, 2, 3, 4 possible configurations. If you are going to take two spins on a lattice, then there can be 4 possible configurations, right? So and each, so we already said that two of these configurations, these two configurations are going to have energy minus J, and these two configurations are going to have energy plus J. Okay, so that we have already discussed in the earlier slide. So now we are going to consider Ising spins on a lattice. Energy associated with this spin configuration C. We are going to say that there are different spin configurations. So I am going to take any one spin configuration. So this is the spin configuration C. Okay. So the energy associated with this configuration C is given as E of C. Okay. So energy associated with this configuration C is given by E of C. Okay, so that is minus J sum over Ij. Ij are nearest neighbors. Si of C, Sj of C. C is the configuration which we are going to take. Minus B. B is the magnetic field, and sum over I, Si of C. So Si is nothing but the spin present on site I. Sj is the spin present on site J. And we are going to take J positive because we are going to consider ferromagnetic interaction, and B is the magnetic field applied, external magnetic field. That value we can take different values. So when the temperature is lowered below a critical value, even in the absence of external magnetic field, the symmetry is broken. Okay, and this is called spontaneous symmetry breaking. So the spins can orient in random direction, which is here plus upward or downward. So when the temperature, so there is a symmetry in this present in the system. So when you lower the temperature, so below a critical temperature, we will find that even without external field, this term 0, we will find that there is a magnetism generated in the material, and there is a symmetry broken. What do you mean by the symmetry broken? Instead the spins orient in different directions, we will find all the spins are oriented either up direction, or all the spins are oriented in down direction. So this up-down symmetry is broken, and this is called spontaneous symmetry breaking because we are not applying any external magnetic field. So it is clear that Ising spin system at very low temperatures will have low energy because aligned spins and large magnetization. So with very low temperatures, all the spins will be aligned into a particular direction, and then that is the reason why when we sum up all the spins or tiny magnetic moment, we will get large magnetization without applying any external field. Only we are going to cool the system. So on the other hand, when at high temperature, the spin system will have high energy because randomly oriented spins, hence no net magnetization. At low temperature, we will find all the spins are oriented in up direction or oriented in down direction. We already calculated that the energy associated with these kind of spin configurations is minus J. So the energy is lower, and there is net magnetization. At high temperature, the spins are going to orient in random directions. They are either going to orient in random direction. The energy associated with these two random directions is plus J. So the energy is high. And there is no net magnetization because all the spins are oriented in random directions, up and down, that is plus 1 and minus 1. So when you are going to add up all these tiny magnetic moment which are oriented randomly, you are going to get zero magnetization. So there is no net magnetization at high temperature. So the system transforms from a disordered ferromagnetic. So this high temperature phase is called paramagnetic state where there is no net magnetization. And the low temperature phase is called ferromagnetic phase. So So the system transforms from a disordered paramagnetic state. So this is a disordered paramagnetic state, and this is a ordered ferromagnetic state. So the system transforms from disordered paramagnetic state at high temperature to ordered ferromagnetic state at low temperature. So the system undergoes a phase transition below a critical temperature called Curie temperature. So Ising solved the model in one dimension analytically and showed that there is no phase transition. So using this using this interaction energy, so Ising solved this in one dimensions. Ising solved this in one dimension analytically and showed that there is no phase transition. So by looking into different macroscopic quantities, for example, magnetization, and they also looked into susceptibility, magnetization, susceptibility, and if there is a phase transition, this susceptibility should show a divergence. But Ising find that there is no divergence in susceptibility or specific heat, and hence there is no phase transition in one dimension. That is what Ising found in by solving this model in one dimension. But under a mean field approximation, the Ising model exhibits phase transition. There is a phase transition by applying mean field approximation. So this raised a serious doubt whether the statistical mechanics machinery can at all describe phenomenon of phase transition. So if you apply mean field approximation, you are going to find that there is a phase transition. But when we solve analytically, we find that there is no phase transition. So that is the reason why it raised a question that whether we can use this statistical mechanics machinery to find to understand whether there is a phase transition in a system on cooling. So after all, one can argue that the phase transition predicted is an artifact of the mean field approximation. So the questions, that is the reason, we are applying mean field approximation. So it is an artifact. The phase transition which we find by applying mean field approximation is an artifact. So this serious dilemma was settled once and for all by Ansager. So the question that the statistical mechanics machinery can be used to understand phase transition in a system is settled, and said that we can use statistical mechanics machinery to understand a phase transition in a system by Ansager. When he solved this two-dimensional Ising model exactly in two dimensions, and it shows a phase transition just like real magnets at finite temperature. So Ansager solved this question or puzzle that statistical mechanics machinery can be used successfully to understand a phase transition when he solved the Ising model exactly in two dimensions, and he found that there is a phase transition that is predicted by mean field approximation. So Ansager showed that the phase transition temperature for two-dimensional Ising system is given by this equation. So we discussed that what is the Ising model and what we can understand by applying this, solving this Ising model, right? So how do we simulate an Ising spin system? So how can we understand this Ising model in a computer simulation? So for example, let P of C denote the probability with which a macro state of an Ising system occurs in a closed system at temperature T. So we are now saying that the magnet is in contact with a heat bath. So we are going to construct a canonical ensemble. Okay, and we already discussed that the probability of occurrence of a microstate in canonical ensemble is given by this. P of C is 1 by Z of beta exponential minus beta E, where Z is the normalization and which is known as partition function, canonical partition function. So this is the canonical partition function, which is a normalization. So, and E of C is the energy of the microstate C. So we say that a Boltzmann weight given by exponential minus beta E associated with the microstate C. So let V be the total number of spins in the system, and it is readily seen that the number of possible spin configurations or number of microstates is 2 power V, because each spin can either oriented in up direction or down direction. So total number of microstates possible will be 2 power V, where V is the total number of spins. Let us consider a simple-minded approach to simulate the system. We shall call this as analog Monte Carlo. So we are going to apply Monte Carlo simulation, Monte Carlo technique to solve this Ising model, and we are going to start with simple technique which is called analog Monte Carlo. So the system consists of sampling microstates randomly. This analog Monte Carlo technique consists of sampling microstates randomly and independently with equal probabilities. All the microstates are going to be sampled with equal probability, and we are going to assemble all these microstates an ensemble of n equally probable microstates. So we are going to assemble all these microstates in an ensemble, and where all the microstates are equally probable, and carry out weighted average Boltzmann weights, which I discussed here. So we are going to take a Boltzmann weight, right? E power minus beta EC. Okay. So take a weighted average of the macroscopic quantity, say magnetization, over this ensemble which we have collected, where all the microstates are equally probable. So this is the weighted average of the macroscopic quantity magnetization. So a real magnetic system would contain an extremely large number of spins, for example 10 power 23, which is Avogadro number. So how are we going to simulate such system? So let us consider a modest model system with some 100 spins on a two-dimensional square lattice. So we are going to consider a square lattice in a 2 dimensions, so 10 by 10 square lattice. So the number of spin configuration is 2 power 100. So we are going to take 10 by 10. So that will be total number of sides is 100, and each side can have either up or down direction. So each spin can have either up direction or down direction. So 10 by 10 lattice. So totally we'll get 2 power 100, which is roughly equal to 10 power 30 microstates or spin configuration. So even if we assume optimistically that it takes a nanosecond to generate a spin configuration, the total time required to sample all the spin configuration is nearly of the order of 30,000 billion years. Even if the system computer is going to generate each spin configuration in a nanosecond, the total time required to generate 2 power 100 or 10 power 30 configuration is 30,000 billion years. Okay, so it's not practical. So in a Monte Carlo simulation, we sample only a very small number of spin configurations, say 10,000 or 20,000 spin configuration with modern high-speed computers. It may be possible to generate a few billion microstates with recent computers. So unfortunately, because of the Boltzmann weight e power minus beta EC, most of the configurations randomly generated would contribute very negligibly to the sum over to calculate the macroscopic property. So associated fluctuations in that macroscopic quantity shall be very large. Hence we resort to another technique called importance sampling. So we find out that if we are going to use simple analog Monte Carlo technique, where we sample all the microstates of this spin system equally probable, then we are going to end up macroscopic quantity with huge fluctuations, and we are not such quantities cannot be compared to an experiment or theory. So we need another technique where we sample only microstates that are mostly probable, which is called importance sampling. Okay, so in importance sampling, the idea is to select spin configurations randomly and independently from the distribution. We are going to sample the microstate from this probability distribution. So this says that it gives the probability of occurrence of a microstate. So we are going to sample microstates independently and randomly from this distribution. Okay, so this is for a canonical ensemble. So these pin configurations, when sampled adequately large number, constitute to a very good approximation a canonical ensemble. So therefore, average of a macroscopic property can be calculated at a simple arithmetic mean over the sampled microstates. So in important sampling technique, the idea is that we are not going to sample all the microstates equally probable, but we are going to sample the microstates randomly and independently from this distribution, probability distribution, and then all the microstates sampled should be adequately large in number, and when we calculate the macroscopic property from these ensemble, the macroscopic property which can be now calculated as a simple arithmetic average will be much better, and the fluctuations associated with this macroscopic property will be very less compared to the macroscopic property calculated using analog Monte Carlo technique. Okay, so to carry out this task, we need to know the partition function z of t, but then z is precisely what we want to calculate in the first place. There is a catch here. But unfortunately, there is a way out as shown by Metropolis and his co-workers. So that is in Metropolis algorithm. When we use Metropolis algorithm, we will find out that there is no need to calculate this partition function, and hence it is not important to calculate partition function. So for that, to use this Metropolis algorithm, we need to construct a Markov chain of configurations. Markov chain. So what is this? And how do we construct? So we need to construct a Markov chain of configuration starting from an arbitrary initial configuration C0. So we are going to start with a microstate C0, and then we are going to sample a microstate from this initial microstate C0. So C1 is sampled, and after a certain time C2, C3, we are going to sample Cn and Cn plus 1, where n is the time index. Okay, we are going to collect now we are going to construct a chain of configuration which we call it as Markov chain. So we establish that for large n is a time index. So for large time, the set, whatever the micro states collected in the set, constitute an equilibrium ensemble. Once we constitute this equilibrium ensemble of microstates, then we have done the job. So in the next class, we will discuss about Markov chain and Metropolis algorithm in detail, and how we are going to calculate any macroscopic property using this Metropolis algorithm and Markov chain. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.